All right. Well, since we cannot have an actual class today, I am recording this lecture ahead of time. So the first thing I want to do is to talk about the assignment that is due today, just functions. Here we go, and then we'll take a look. And I will do a preview, so I am going to do the test or the assignment the same way that you would otherwise. All right, question number one. It is asking what is the Cartesian product between x and y. So in this case, the Cartesian product is going to be a set. So you have to start with a brace, and then you can list the six individual two tuples, okay, like so. So you can do this in any particular way, but this is probably one of the easier way to do it. And then A3, and then B3. There we go. All right, so that would be the answer of question number one. For question number two, based on the previous question, what is the cardinality? It is 6. And then number three, reference the definition of x and y in the first question. Enumerate all sets that can be considered functions using x and y as codomain. And you can consider writing your own program to generate this answer. However, using someone else's code or asking AI for an answer is self-defeating. For this answer, use one line for each set that can be considered a function using x as a domain and y as a codomain. All right, so it's actually kind of systematic too. So the template that we're working with is A has to map to something, B also has to map to something. So this is basically the template. And once we have the template, okay, I'm just using copy and paste here. So now we can go like, okay, they can both map to 1. So they can both map to 1, and they can both map, one map to 1, one maps to 2, and then one maps to 1, one maps to 3, like so. And I'm not sure why it is, why this line spacing is off. Okay, maybe that will change it. Okay, so once we have this template, we can just copy and paste it like 3 times. And because all we have to do is to change what A is mapping to. So, all right, so let me go all the way back here. The template is no longer needed. So for the next 3, we map A to 2. And then for the last 3, we map A to 3. There we go. 3, 3, and 3. There we go. So altogether, there are 9 of these sets. So there we go. And question number 4, based on how x and y are defined in the earlier questions, how many subsets of x and y are not functions? In other words, what is the cardinality of a set that we are creating in which every element is an f, such that f is a subset of the Cartesian product between x and y, and it is not the case that f is a function from x to y. So that's basically the same thing as what the English is describing. So in this case, we know that there are only 6 that are functions. So now the question is how many uh, subsets there are. So we talked about the subset idea earlier in the semester, and then we talked about how if there are um, n elements in a set, the total number of subsets that we can generate would be 2 to the power of n. So in this case, there are 6 elements in the Cartesian product. So that means we have 2 to the power of 6. That would be 64. So there are 64 subsets, of which 9 are actually functions. So 64 minus 9 is 55. All right, so this is a 55 here. And I think that's it. All right, so submit quiz. And there are some questions that needs to be graded um, because they are like this one, has to be graded later. This one is 1 out of 1. This one also has to be graded manually. And then this one is 3 out of 3. So I think that's the best I can do um, without having to manually grade some of the other answers. All right, so now we can go ahead and talk about a new topic. So the new topic is, okay, let me close this right there. The new topic is about Aleph Null, and we're going to go take a look at Aleph Null. So the Aleph Null module is this one. We already kind of talked about the set of natural numbers and the cardinality thereof, and we are now defining what the symbols, corresponding to the cardinality of the natural numbers and the cardinality that is corresponding to the set of all integers. And both of these are the same, so this equality sets the cardinality of the set of all integers is the same as the cardinality of all natural numbers. And the cardinality of the set of all natural numbers is known and defined as Aleph null. So this symbol here is Aleph, and the null is the 0 down here. So this is established by having a bijection. Okay, f is a function, but in this case, it has to be a bijection that is mapping from the set of all integers to the set of all natural numbers. And the way it is done is by um, looking at whether x as an integer is positive or not, or I should say whether it's negative or not. If it is not negative, meaning it is greater than or equal to 0, it maps to 2x as a natural number. If x is negative, then it maps to negative 2x minus 1 as the integer that they map, as the natural number that it maps to. So you can probably just kind of go through a few examples and find out, how this works. Um, so in this function definition, I'm using the ternary operator in C and C++. So if you're not familiar with the ternary operator, you can look it up and find out, how to read the ternary operator. It is well documented in any C or C++ textbook. Right. So we are now looking at the properties of this particular function. So what this is going through is to prove that f is injective, and the next question is it surjective. So that means, do we guarantee that all elements in N are mapped to? One way to do that is to simply look at an inverse function. So this is the inverse function of the f that we looked at earlier. So in this case, x is a natural number, and we are going back to see which integer is corresponding to this x, which is a natural number. So we basically what we do is first check whether x is a even number or not. Because if x mod 2 is 0, that means x is a even number. In the case that x is a even number, then the integer that this natural number x maps to is going to be x divided by 2. On the other hand, if x is not a even number, then what we do is we first add 1 to x, because remember x is a natural number. So we add 1 to x, so x becomes a multiple of 2, and then we divide it by negative 2, mapping it to a negative integer. So this particular f inverse would actually work as the inverse function of the f that we defined up here. And because f is bijective, so now we can claim that n and z, the set of all natural number and the set of all integers have the same cardinality. And this is a really short section. It talks about infinitely countable. The cardinality of the set of all natural number is infinite, but it is also called countable. There are sets where the cardinality is not countable. For example, the set of all real numbers is not countable. So essentially, it is saying, we have certain classes of sets, and there are many classes that share the same property as the set of all natural number. Essentially, everything that has a cardinality of aleph null are known as infinitely countable. So now we want to see what else is countable. For this part, it is easier to show it using a graphical method. So I will go ahead and show it in a graphical method in just a little bit of time. All right, so this is the part that it gets a little bit tricky for me because I have to keep wearing my uh, 3D goggle to, um, so I have the mic attached, and I have to look at my tablet instead of my virtual screen at the same time. So I think I can get this to work. It's okay. I think I got it. Anyway, so what we want to do in this case is to look at the cardinality of the Cartesian product of natural number with natural number, and we want to compare that to the cardinality of just a set of natural numbers. So we want to ask, this is a question. We want to ask, is that equal? Okay, does the cardinality of natural number Cartesian product with natural number, does it equal to the cardinality of just natural number? So you look at this and go like, that is kind of interesting, right? Because one is a two-dimensional space. The one on the left is a two-dimensional space, and the one on the right is a single-dimensional space. And how can that possibly be of the same dimension? So what we want to do, there are quite a few steps ahead of us. So I will kind of describe these steps, step by step. So the first thing is, we are going to take a look at a way that intuitively works. Okay, we can map in one direction at least. So what we're going to do is to look at a function g in this case, and function g is going to take the Cartesian product of the set of natural number with the set of natural number, and it will map it to just a set of natural number. So we're going to take a look at a g function like this first, and we'll take a look at the g function in an intuitive way at first, and then we'll go ahead and formalize and basically look for the closed form of this particular g function. So the best way to describe this g function is to think of it like this. Okay, so if I am to draw a two-dimensional space like so, uh, the first cell over here would be at coordinate 0, 0, and then we have this is going to be at the x-axis will be 1, the y-axis here would be 1, and then this would be a 2, this would be 2, this would be 3, 3, a 2, 1, 0. Okay, and we'll just kind of make this up to, yeah, we'll make it up to 4. Okay, like so. There we go. All right. So the way we're going to do this, okay, let me just kind of now indicate this is the x-axis and this is the y-axis. There we go. So the way we're going to fill in these cells with natural number is to sweep in a diagonal way. We'll start 0 here, and then this is 1, 2, and this is 3, 4, 5, and then we have 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. So the diagonal is basically we are sweeping in this particular way. Okay, we are sweeping from lower right to upper left as a diagonal. And then when we run out of diagonal space, then we go back to the base of the x-axis and then start again. So this is the way we're going to fill up. So in other words, in this particular example, I can tell you how we map particular values. So let's just say that we look at this one here. Okay, this is the cell that we're looking at. So this particular cell, okay, has a coordinate of 2, 1 as its your coordinate, and the natural value that the then natural number value associated with it is 7. So that's how a particular coordinate is mapped to a single natural number. So for kind of practical purposes, we can kind of see how this function is um, injective. In other words, given two different pixels, they are guaranteed to have two natural numbers. And that has to do with, the sweeping action is always incrementing the counter as we perform the sweep. So that part is kind of intuitive that it is injective to begin with. But we can also tell that it is surjective because if we keep sweeping like this, we can go to any particular cell in the two-dimensional space and we just go like, oh, eventually, we can sweep all the way up to that cell and assign a natural number to that cell. So that means we can sort of prove that this g function is bijective without using any mathematic proof. So the next thing that we want to do is to say, okay, but this method of finding the natural number corresponding to a particular cell is not very efficient because if I want to find out, let's say g of 300 comma 600, that means we have to kind of map out a lot of cells in order to find the natural number corresponding to that particular cell, and that is not efficient. So we want to find a closed form corresponding to the way that we are mapping these values. So I think we don't need the tablet anymore. So I'm going to go back to my notes because the rest are really just math. So we're going to go back to the notes here. This is all basically corresponding to what we saw earlier. And we can see how g of 2, 1 has a value of 7. All right, so the next question here is how do we find a closed form as much as we can so that given a particular coordinate which has a x and a y and both are natural numbers, we can actually find the natural number corresponding to that cell. So the way to do that is to first recognize that everything on the first row is going to have the g value of anything on the first row, because you can see how y has a value of 0 and x is really just the x coordinate. So whatever this x is the summation of 0 plus 1 plus 2 all the way up to and including x itself. All right, so let's go ahead and check whether this works or not in our actual example. So in the example here, the furthest we can get is 3, 0. So we ask, is 6 the same thing as 0 plus 1 plus 2 plus 3? And the answer is yes, okay, because 0 plus 1 plus 2 plus 3 is exactly 6. What about the other one, which is 2, 0 here? 0 plus 1 plus 2 is in fact a 3. So we can kind of tell that it makes sense. And in terms of the sigma notation, it will turn our g of x0, or the coordinate of x0, is going to map to a natural number that is, based on this sigma notation. So this sigma notation is basically saying we have a loop. The loop starts with I being 0, initialized to 0. The loop has to go through the last iteration when I equals to x, and then the value that we are adding for each iteration of the loop is I. And what we have here is a long derivation, and you don't really have to read the entire derivation, but I think you should be able to understand the derivation because it's algebra here. So that means, if you go all the way to the end here, it means, it doesn't matter whether x mod 2 is 0 or not. They all boil down to x times x plus 1, the whole thing divided by 2. So the first thing we want to do is to plug this closed form back in and ask, okay, does that actually give us what we need? So we go all the way back to this one here, where x is 3. So what is 3 times 4, the whole thing divided by 2? Oh, it really is 6. So it does work out. It's important to plug it back in just to make sure that we did not make a mistake in the process of deriving this. Now, obviously, I included the entire derivation because I thought it is kind of important. So the way this works out is to see if there are an even number of terms that we are adding, or versus there is an odd number of terms that we are adding. Excuse me. If x mod 2 does not equal to 0, x is an odd number. When x is an odd number, because we start from 0, so that means there is uh, um, the same number of items, up to and including x minus 1 divided by 2. And the second half has the same number of items. The second half starts with x minus 1 divided by 2, the whole thing plus 1, all the way up to x. And then what we do is we merge these two together. So it goes from here to here. And then once we have this equation, because I is cancel out here, because I is here, but I is also a subtraction of I is here. So that means we're only adding x. So that means we're adding x, the number of times that we have to go from 0 to x minus 1, the whole thing divided by 2. And that means we have um, x minus 1, the whole thing divided by 2 plus 1 iterations of adding x. So that becomes x times x plus 1 divided by 2. On the other hand, if x is an even number, then there's a middle element that is only by itself, and then the left-hand side of that one element is going to be uh, accounted by this particular sigma notation. Everything to the right-hand side of that middle element is taken care of using this sigma notation. So the difference is x divided by 2 is singled out. It is not a part of any sigma notation. So that means we have, uh, and then we do the same trick with these two sigmas because they have the same number of items. So we merge the two back into one, and then we pull the same trick as the other side. But in this case, because the count that we have, the number of times we have to go through the loop is x divided by 2, the whole thing minus 1. So that means the total number that we have to go through the loop is exactly just x divided by 2. And but we have to add this x divided by 2 on the outside, but eventually it becomes the same as x times x plus 1 divided by 2. So this proof is, as I said earlier, once I have presented the proof, I can't really ask it in an exam, um, but it is important that you know that you can probably do this derivation yourself too, because there's no really tricky math involved, in this proof, other than the use of sigma. Since this is not in a particular class, Well, I shouldn't say that, but because this is not an in-person class, I can't really ask whether people understand the sigma notation or not. So if you have an um, have a question about the sigma notation, then I suggest that you go back to this note here and go to the big operator notes, which is up when we talk about sets. So it's under set notation. I believe it is this one, big operators. So when you open the big sigma, the big operator, then you can go back to the sigma notation. And the sigma notation is, let me see. There we go. So the sigma notation is explained here, and this is the final form of the sigma notation. This is the original sigma notation. F of I is really just how the expression that we need to add um, is expressed. So that means I use function f here just as a general function to describe how the value that we need to add for each iteration depends on the index variable I. The index variable I has to start from B, it has to end with E. So this expression is the same as this ternary expression here. This is a ternary expression because we can see there's a question mark and there's also a colon. If B as a beginning index is greater than the end index, that means there's nothing we are adding because the end should be greater than or equal to the beginning. So if the beginning is greater than the end, that means the sigma notation returns a 0. On the other hand, okay, this is else. We know that there's at least one item that we have to add. So we know that B, which is the beginning of the range, needs to be evaluated using f of B, and f of B has to be at least a part of the total, the answer of this sigma notation as a whole. And then we just add it to another sigma notation. The difference between this sigma notation and this sigma notation is simple. The beginning point is shifted by 1. You can see how this one starts with B. This one says, oh, I already took care of the case of B, so now the sigma notation can start with B plus 1. So you can see how this recursion is going to gradually increase the start index until it is no longer less than or equal to the end index, in which case the recursive definition will return a 0, and then we just backtrack and we get the answer that we need. So I hope this explains the sigma notation, getting back to this context here. So knowing the base of the um, of the matrix that we saw a little bit earlier. So now the question is, what if I'm interested in the natural number that is not on the base or not on the x-axis? What if the index, or what if the pixel is somewhere else? So the trick to do that is to understand that once you know where the base is, we can see how we are just incrementing along the um, along the diagonal line in order to get to the item that we need to get to. The other thing that we can also recognize is if we add the x and the y coordinates of pixels of the same diagonal line, they should add up to be the same. Let me explain that in just a little bit. Okay, so I can actually okay, we can do it this way. So I'm going to use the tablet again. All right. So so this is diagonal line 0, and there's only one. On diagonal line 1, this pixel, the one that I'm waving the little circle over, this one has a coordinate of 0, 1, because it's on row 0 and column 1. But 0 plus 1 is a 1. This is the other pixel on the same diagonal line. It has a coordinate of Um, this one has a coordinate of 0, 1. This one has the coordinate of 1, 0. So I might have misspoken. Let me say that one more time. So this one has a coordinate of 1, 0 because the x coordinate is a 1, the y coordinate is a 0. But if you add the x and the y coordinates, it is 1 plus 0, which is 1. When you look at this particular pixel here, its coordinate is 0, 1. But when you add the x coordinate, which is 0, and the y coordinate, which is 1, 0 plus 1 is still 1. When you look at this one, the sum is 2. When you look at this one, the sum is 2. When you look at this one, the sum is 2. The sum is now 3, 3, 3, 3, and then 4, 4, 4, 4, 4. So this observation allows us um, to figure out the g value. Okay, in general, it looks like this. If you're looking at, the coordinate of xy like this, then this particular g value is really the same thing as the g value of um, the base of that diagonal line. So the diagonal line that we're looking at is x plus y as the x coordinate and y as the x and 0 as the y coordinate. So this would be at the very base of that diagonal line. And then what we need to do is simply to add y to this value because this is the number of times we have to step up or take the stair up. So that becomes this number here. And then because of that, this becomes x plus y, the whole thing times x plus y plus 1 divided by 2 and then plus y like that. So if you are not really sure, that this works, what you can do is to pause the video first, and then just kind of plug in the values of specific cells that already have the values worked out, and just kind of verify to yourself that this particular equation works out, because this is how this is the closed form of how we compute the natural number corresponding to a two-dimensional coordinate of something like this. All right, so we are going to proceed next to the, oh, okay, I guess we have to charge the tablet now. All right, so what we will do next is to look at the inverse function now, because what we have done is we worked out the baseline, we worked out a general cell, and now what we need to do is to reverse the whole thing. So what we need to do in order to reverse the whole thing is what we are trying to do is to figure out the inverse function, which is g inverse. And the way this works is you give it a single natural number, let's say n, and it has to return a coordinate of x, y, and x has to be a natural number, y has to be a natural number. And the way we get this to work is by using a inequality. So if we assume and define w such that w is x plus y, so w is basically the ID of the diagonal line where the pixel is supposed to be. Because when we know that for every pixel on the same diagonal line, the sum of the x coordinate and the y coordinate should add up to be the same. So based on that observation, we know that g of w0 is defined to be w times w plus 1 divided by 2. That was shown earlier when we were working out this part here. So now that we know that, we also know that because n is not um, corresponding to, well, not always, it's not always corresponding to a pixel at the base, which is the x-axis. So that means the actual natural number corresponding to xy can be more, which is n here. So now we have an inequality. The inequality is w times w plus 1 divided by 2 has to be less than or equal to n itself, like so. So by using a few algebraic step, we get it to something that looks like this. So that is not a quadratic equation, it is a quadratic inequality. So because it is an inequality, that means the w has two roots, by the way. Because w has two roots, one is positive and one is negative, we can basically automatically throw away the negative root because w has to be non-negative because w is x plus y, x is a natural number, y is also a natural number, so w has to be a natural number as well. So w has to be non-negative, which means out of this the root, which is this operator has to be a plus or a minus. So we're only focusing on the plus because that's the only way we can end up with a non-negative root. So that means we are only focusing on the plus here, and as a result, um, and also one more thing, because the square root will give you a irrational number in general. And as a result, we also have to use a floor operator here. The floor operator is important because we are looking for the largest natural number that is less than or equal to whatever we are taking the floor of, because we need to make sure that this equation or this formula on the left hand side remains less than or equal to 0. Without the floor operator, we would end up with a w that is a irrational number that makes the left hand side of the less than or equal to exactly the same thing as 0. But because we need w to be a natural number such that the left hand side of the less than or equal to is actually less than or equal to. So that means your w cannot be just equal to this whole thing. It has to be the floor of that thing, whatever is that we are taking the floor of. So once we solve for w, the rest is relatively easy because what we can do is then we can figure out y as n minus w times w plus 1, the whole thing divided by 2. And this is the derivation. The derivation is basically saying, okay, if we knew the x and the y, then n equals to the result of this formula here. And then substituting your w being x plus y, we can simplify that to become something like this. And once we know that n equals to w times w plus 1, the whole thing divided by 2 plus y, because at this point n is known, w is also known. So when we throw all the known terms to one side and leaving y as the only one on the other side, we can now solve for y. Once we can solve for y, we can also solve for x because we know that w by definition is x plus y. So now we can also solve for x over here. So in general, the way we look at the inverse function, the best way to do it is to look at Wn as this. We look at W not as a constant, but look at it as a function. So Wn as a function is defined to be the floor of the non-negative root of the quadratic inequality that we have. And once we have this defined, then we can go ahead and define the rest of this. Basically, we just make use of what we figure out earlier, which is this part here, and then we end up with this equation here. G inverse applied to a natural number n is going to be a two-dimensional coordinate This is a two-dimensional coordinate expressed as a two-tuple. The first item of the two-tuple, which is the x coordinate, is going to be wn times wn plus 3, that whole thing divided by 2, minus n. And then the second item is going to be n minus wn times wn plus 1, the whole thing divided by 2. It looks kind of tedious, but it works. And I strongly encourage you to um, experiment with this. Okay, just plug in some known n here, and then reverse it back to the two-dimensional coordinate. And one way to do it is to look at this. Okay, just plug in this 8 here or the 12 over here. Okay, plug in 8 as n, and then try to figure out whether it returns a coordinate of x being 1 and y being 2. Um, or you can use some other one like the 11 here. So if you plug in n as 11, you should end up with x being 3 and y being 1. It is particularly important that you understand how to apply the inverse function of g, because that is going to be in the exam. Well, I think it's going to be in the first exam, because now that we have talked about it, we can actually have it in the first exam. So the importance of this is we can now show that the cardinality of the Cartesian product between a natural number set and a natural number set is really the same as the cardinality of the natural number set itself. But that's not the only significance about this, because you can repeatedly do this and fold a two-dimensional space into a single-dimensional space, but then that means you can start with a three-dimensional space and then fold it twice into a single-dimensional space. Or you can start with a four-dimensional space and then fold it three times into a single-dimensional space. So that basically says if you have a finite dimensional space, and each coordinate, each dimension is a natural number, that whole hyperdimension can be folded into a single dimension of natural numbers. So I think that is somewhat fascinating, even though, based on the mathematics that we have talked about, is not super mysterious, but it is still kind of interesting to see. All right, so now that we are done with this is actually, oh, by the way, this is also called the Cantor mapping function. So now that we are done with this particular topic, we are moving on to talk about the next big topic. It is about relations. So this is the relations topic, and we're gonna get started here. Okay, there we go. All right. So a relation is essentially a subset. Okay, there's no actual restriction, you know, that it has to satisfy certain requirements like a function does. So a relation only has to be a subset of the Cartesian product of the set that the relation is defined on or over. So the way we call a relation is that it is defined over a particular set X, because what it does is it expresses whether an element of X is related to another element of X. So this is the way it works. And there are a few ways to interpret this. I mean, it sounds really abstract, but it's not really going to be as abstract as it seems. Okay, so we can kind of go through a few examples, and I'm going to use my tablet for that purpose. Okay, so we'll wake up the tablet like so, and then we will proceed to talk about um, examples. So let's just say that X is a set of 1, 2. Okay, so there's not a whole lot in X here. And R is defined as just 1, 2, like so. So that means, 1 relates to 2 using R, but not the other ones. So we can now say, 1, R, 2, is true, 2R1 is false. So we can now see how why the tuple is important. It is not a set because 1, 2 as a two tuple means 1 relates to 2. Excuse me. It does not say that 2 relates to 1. It is not automatically going in the opposite direction. We can also say that R1 is false. 1 does not relate to 1, and then 2R2 is also false because 2 does not relate to 2. So that's how we look at a relation, and this particular notation is simply saying 1, 2 is a two tuple in R. So we can now also say that this means the same thing as 1, 2 as a two tuple in R is true. So they mean exactly the same thing, except this notation is a little bit handier. Okay, it's easier to write compared to this notation over here. So now that we have talked about the general notation of a relation, the next question is why is it useful in computer science? Because it looks pretty arbitrary as a definition. So the question is why is it important in computer science? So the one thing that is really important in computer science is whether something is sortable. The concept of whether something is sortable or not is important because if something is not sortable, and we'll kind of talk about what that exactly means that we cannot find the most something about um, a group of items. Um, let's think about we're trying to define a function so that we can rank video game players. Um, and we want to find the player of the week. Okay, so we want to define a function so that we can compare a gamer with another gamer. And there are ways to define such a function in a way that it does not meet all the requirements in order to use this function for sorting. So if this function does not support sorting, then we cannot really find the gamer of the week because we might end up with several gamers who are also who can be considered as mm, the most important player in relation to only certain subgroups of other players. But there's no particular way to compare between these specific gamers. Um, it's harder to actually give you an example, in at least at this point, about how that is important. Um, but what we can also do here is to use a concrete example. So in this case, I'm just using the usual less than relation in C++. So when you use the less than um, operator in C++, the less than operator is known as one of the relational operators because it relates two integer values. So what we can say is 1 is less than 2 is true. Okay, this everybody knows this. But the alternative way to say this is 1, 2 as a two tuple is an element of the really strangely named set. Okay, the name of the set is less than. Okay, but that's just a notation thing. Okay, nobody says less than cannot be used as the name of a set in this class. So basically, we can look at the relational operator in the sense of just a straight up relational operator in terms of syntax, or we can look at it as a set of two tuples, where if 1, 2 is an element of the set, that means 1 is less than 2, if and only if 1 is less than 2. And then there are some random examples here. Okay, so the random example is not particularly useful in any way other than illustrating the concepts. So if we define X as A, B, C, D, and we define R as a relation over X as AA, AB, BC, DD, BA, then we can say ARB is true because AB is a two tuple in R. We can say BC is an element of R is true because BC is actually an element of this set R. We can say that BRB is false because BB is not an element found here. So B does not relate to B uh, using relation R over X. We can also see DC is an element of R is false. In other words, we are looking at R as a set in um, when we use the element of operator, and then we look at R as a relation when we use BRB or ARB, in those notations. So R is the only relation that can be defined over X. Is not, okay, it is not the only relation that can be defined over X because X cross X, okay, the Cartesian product between X and X in this particular case has 16 elements because X itself has 4 elements. So the Cartesian product is going to have 16 elements. According to the power set calculation, that means the total number of subsets of the Cartesian product of X and X is 2 to the power 16, which is 65,536. So that's the total number of relations that we can actually define over X. Now, many of those can be useless, but nonetheless, every single one of those can be seen as a relation. As I talked about a little bit earlier, a relation, unlike a function, does not have a particular requirement that every element of the domain has to map to one and only one element in the codomain. So without that restriction, any subset of the Cartesian product in this case is a relation. The only question is, do those relations satisfy certain requirements to have certain properties? All right, so now we're going to take a closer look at some of the properties of a relation. So the first one is reflexive. Reflexive is basically asking the question of um, does every element of X relate to itself using R as a relation? If so, then relation R is said to be reflexive. All right, so we will take a look at this and see how we can evaluate some of the examples. So instead of using the tablet, I think this part here is easier to illustrate just using a text editor. So let me go ahead and do that. Accessories, and then we look at mouse pad. All right, all right. So we are going to define x to have, 1, 2, 3. Oops, 1, 2, 3. All right. So in the case of R being an empty set, is it reflexive? Okay, so I'll give you a few examples and then we'll go ahead and answer the questions. So this one is just 1, 1. And then this one is 1, oops, 1, 1, 2, 2, 3, 3. And then finally, oops, this one is 1, 1, 2, 2, 3, 3. And I'll throw in a 1, 3. Like so. Okay. So we'll look at each one and ask whether it's reflexive or not. This one is not reflexive because we can see how 1 does not relate to 1, 2 does not relate to 2, and 3 does not relate to 3. So it's not reflexive. This one is also not reflexive because even though 1 relates to 1, but 2 does not relate to 2, and 3 does not relate to 3, you have to pay special attention to the quantifier because the quantifier here is a universal quantifier. It means for every element in X, this has to be true. And even though when E equals to 1, this expression is true, not so much when E equals to 2 or 3. And because the universal quantifier requires every subcase to be true, so that means this is not reflexive. This one, on the other hand, is reflexive, and this one here is reflexive as well. So reflexive is interesting because you can have some additional elements, such as your 1, 3. It does not even matter because all we are trying to find is 1, 1, 2, 2, 3, 3 in this case, in order for this R defined over X to be reflexive. Having some additional elements in the relation, as long as the relation, the set R, is still a subset of the Cartesian product of X with itself, it is still reflexive. So now we can move on to the next property, which is about symmetry. So this is the quantified expression to qualify symmetry. It says for every E and F in X, EF as a two-tuple in R, if and only if FE in R is required in order for R to be symmetric. Okay, so we are going to go back and take a look at these examples here. This one is actually reflexive. This one is actually symmetric. Symmetric. And this one is also symmetric. This one is also symmetric. And this one is not symmetric. All right, so let's go take a look at why the first one is symmetric. So this one here, okay, let's take a look at this one. Why is this case symmetric? In other words, R is an empty set. So if R is an empty set, how can it possibly symmetric? So the key here is to understand the operator if and only if. So and then you have to look up the truth table of if and only if. And then you have to ask, if R is an empty set, this element of has to be false. But this element of also has to be false. So that means no matter which E and F of X we are looking at, EF is an element of R is guaranteed to be false. So we basically are looking at the result of false if and only if false. And now you have to ask the question, what is the value of false if and only if false? To answer that question, okay, you have to go back to the operators. So that means it will be very helpful if you have already mastered the operators and have your own kind of lookup table of the operators, because that's something that we talked about in week 1 in particular. It's the first day of the entire semester. If and only if is also called equivalence. And in this case, you can see that if x is false, y is also false. False if and only if false is actually true. So this table shows us why. Let me go back to here. So this table is showing us why when R is empty, it is actually symmetric because both sides of the if and only if have to be false. But it also makes this one false, and it also makes the second example symmetric because in this case, the only element that we can find in R is 1, 1. So that means if E is 1, F is 1, then um, the if and only if is true because EF in R, if and only if FE in R has to be true. But for other values of E and F, it is not in R, and therefore we end up with false if and only if false, which is still true according to this truth table. This one here is not symmetric. This one is not symmetric because when E equals to 1 and F equals to 3, then we have the asymmetry. Because what we end up with in that case is 1, 3 is in R is true, but 3, 1 is in R is false. So that means we are looking at the third line of this table here because we basically see that 1, 3 in R is true, but 3, 1 in R is false. So now we have true if and only if false, which is false over here. All right, so let's go back to the relation notes here. So what this means is the mastery of knowing the operators is actually really important in this case, okay? Because we are building up on top of previous concepts in this class, and we are essentially making the assumption that once we introduce an operator, you would have written it down and understood the operator so that we can apply and use those operators in other definitions. Now we're looking at transitive. For every way to choose E, F, and G as element of X, if this requirement is true, then the relation R over set X is known to be transitive. So the way it works is in this case, basically we are saying if EF is in R and FG is in R, it implies EG is in R. That is what transitive is, how transitive is defined. So what we'll do is we're going to work out a few examples and use some existing examples too to illustrate this concept. So we'll go ahead and take a look. This one is actually transitive. When R is empty, it is also transitive. The reason why when R is empty, it is transitive is because, okay, let me see if I can, yeah, I can do this, is because when R is empty, then EF in R is guaranteed to be false, FG in R is also guaranteed to be false. False and false is guaranteed to be false. Well, if the left-hand side of the implication is false, then the implication itself is guaranteed to be true. So that means, I don't even need to know whether the right-hand side of the implication is true or not. We know that the implication is guaranteed to be true. So that is the reason why when R is empty, it is known to be transitive already. This one is also transitive. Um, this one is definitely transitive. And this one is transitive as well. All right, so let's take a look at something that is not transitive. So we can define R to be 1, 2, and 2, 1. This is not, so we can go for all of the other properties as well. This is not reflexive because 1, 1 is missing, 2, 2 is missing, 3, 3 is also missing. It's definitely not reflexive. On the other hand, it is symmetric because 1, 2, if and only if 2, 1 is true, and then if we use any other two values, then both sides would be false. So it is symmetric and it is not transitive. Okay. So the question is, why is it not transitive? It is not transitive because all we have to do is to put in E being 1, F being 2, and then G being 1 again. Okay, so if those are the values of E, F, G, then we can see EF in R is true, FG in R is also true, but at the same time, EG, which is 1, 1, in R is false. So this time we managed to make the left-hand side of the implication true, but the right-hand side of the implication to be false. So that's why it is not transitive. So transitive is a little bit harder to spot, or I should say, something that is not transitive is a little bit harder to spot because there are more test cases that you need to consider to figure out whether something is transitive or not. The next one is confusing in a way because it's called anti-symmetry, which is not the same thing as not symmetric. So the most important thing about this class is you typically want to go back to the definition and not to use a intuitive way to understand the terms because the definition is has a lot more clarity to it. So anti-symmetry is defined to be for every way to choose E, F as elements of X, E, F in R, and F, E in R implies E and F are the same. Okay, so once again, we have an implication here. The implication is important because if the left-hand side is guaranteed to be false, we know that the implication is true, which means the anti-symmetry is going to be true again. So now we can go back to all the examples that we have seen here. This one is anti-symmetric. It is anti-symmetric because R is empty, which means the uh, value on the left-hand side of the implication is guaranteed to be false. Let me show you which one I'm talking about here. E, no matter what you choose as E in X, no matter what you choose as F in X, EF in R is guaranteed to be false because R is empty. FE in R is also guaranteed to be false. So that means you have false and false on the left-hand side of the implication. According to the truth table of implication, that means the implication itself is guaranteed to be true. So that explains why when R is an empty set, it is guaranteed to be anti-symmetric. This one is actually anti-symmetric. Anti-symmetric. This one here is anti-symmetric. This one here is also anti-symmetric. This one here is not anti-symmetric. It is not anti-symmetric because what we need to do is to say E equals to 1, F equals to 2. So if E equals to 1, F equals to 2, we can see how um, 1, 2 in R is true, 2, 1 in R is also true, but we can also see, how 1 equals to 2 is not true. So now we end up with the left-hand side being of the implication being true, but the right-hand side of the implication being false. So that's why, in this particular relation, it is symmetric, but it is not anti-symmetric. All right. Um, these are, these definitions or properties of a relation can be a little bit tricky to understand. And the best way to practice is to use AI to help you. And there are a few ways to do it. Okay, so let's go ahead and take a look at a few ways to do this. And typically, what I do is, I have some AI generated examples already. So we can take a look at a few ones like this one here. Is it reflexive? No. Is this symmetric? Yes. Okay, these are too simple. These are, by the way, these were generated using ChatGPT like a long time ago. So that means you can now start to use better AI models to come up with better examples. So let's go ahead and copy source to the clipboard. And then what we do is we go to Gemini. Gemini, there we go. And then what we do is we upload, whatever we have just copied. Okay, so we uh, ask it like this. Um, I am including class notes related to relations as follows. Okay, and all I did here was to paste from the paste buffer. And I forgot to do one thing, and I forgot to say that, well, this is okay. I can just click play. And then I'll ask it, to generate a few questions. There we go. Oh, it doesn't like that. Okay, give it one more time. Oh, it says question number 8 is a hallucination. All right, let's check out question number 8. Is the relation less than on the set of integers a total order? The answer is no. Ah, okay, so it is incorrect. Okay, this is incorrect. It is not a total order, but that part we can talk about later. Um, but first of all, I wanted to generate some other questions first. Okay, so we'll say, okay, generate questions to test my understanding of reflexivity, symmetry, anti-symmetry, transitivity, and transitivity of relations. And we'll limit it to say 8 questions. Okay. There we go. The capability of an AI generating questions like this actually has been improved quite a bit over the past even 2 years. Um, and as a result, this is a great way to study for class, is simply to ask the AI to generate some questions. Um, all right, so we'll start with the first one. It has already generated all 8 questions here. Suppose we have a set x equals to 1 to 3 for a relation R defined over x to be reflexive. Which of the following sets of order pairs must be a subset of R? So it will be this one here. I don't understand what the house is, you know, why that is here, but that's the correct answer. Okay, number 2. If a relation R is defined such that for any EF in X, EF in R implies FE in R, which property is being described? Oh, that's an easy one. It's about symmetry. So this one is answer D, symmetry. There we go. Number 3, consider a set of integers z and a relation R defined as x or y if and only if x is less than or equal to y. Why is this relation anti-symmetric? All right. So it goes back to the anti-symmetry definition, which is if x is less than or equal to y and y is less than or equal to x, then it must be the case that x equals to y. So that is the answer because that works out for integers. There we go. And then the empty relation R is R being an empty set. So this is the empty set symbol that we talked about a few times. I typically do not use it, but the AI knows about it and decides to use it. So this is the empty set. Over a non-empty set X is often considered a tricky case. Which of the following is true about the empty relation? It is symmetric, it is transitive but not reflexive. That's one potential answer. It is also anti-symmetric, but it is not linking this one to this one here. So we're going to have to answer this one as the only correct answer. All right, moving along. Let X be ABC and R is AB, BC, AC. Which property does R possess? It is, we haven't really talked about total ordering yet, but it's not. It is not symmetric because if it was symmetric, then we would have BA in it, CB in it, and also CA in it. It is not reflexive because AA, BB, CC are all missing. So it is transitive. There we go. And moving on, what is the key difference between a partial order and a total order? So once again, we haven't really touched on partial order versus total order yet. Um, a total order requires that every pair of elements must be comparable. That is actually the correct answer, but we haven't talked about it yet, so we'll get back and talk about partial ordering versus total ordering. A relation R is anti-symmetric um, if EF in R and FE in R implies E equals to F. If R is 1, 2, 2, 3, 1, 1, over the set 1, 2, 3, is it anti-symmetric? The answer is yes, it is anti-symmetric. Although okay, let me see. The explanation is the trick here. Um, it should be answer A, because there's no distinct pairs, EF and FE both in R. Um, but the way it says distinct pairs is a little bit tricky because it implies E and F cannot be the same. That's basically what distinct pairs means in this case, because we can make those tuples exist by making E and F being ones at the same time. But that would make EF and FE being exactly the same two tuple, which means those pairs are no longer distinct. So answer A is the correct answer here. All right, moving along to the last question. Okay, there we go. In the context of the relation is a sibling of, which property is typically violated, preventing it from being an equivalence relation or an ordering? All right, so let's take a look at each one here. Okay. Transitive is actually, it works with siblings. If A is a sibling of B and B is a sibling of C, A is a sibling of C. So that's why transitivity is not the correct answer. I think the answer is symmetry, which means wait. Symmetry works too because if A is a sibling of B, then B is a sibling of A. Okay, so that actually works if and only if B is a sibling of A. Anti-symmetry is true as well, okay, because um, if we consider a self cannot be a sibling of the same person, then anti-symmetry actually works out because when we say somebody is a sibling of someone else, it cannot be the same person. So that means, yeah, so it just works out that way because we cannot have essentially, we cannot have, like tack is a sibling of tack, and tack is a sibling of tack, and therefore tack equals to tack. That doesn't work. But for any other sibling, then the equality is not going to hold, which means the um, hmm, okay, so anti-symmetry may actually be, wait, we know reflexivity is probably the correct answer, but I'm still trying to understand why I don't want to answer with anti-symmetry because it's looking for something that is not, uh, that does not hold true. Okay, so let me double check with anti-symmetry. So let's just say that we are talking about A being a sibling of B, and because it's symmetric, so B is a sibling of A, and that implies A and B are the same. Is not going to work out because they are A and B are actually two different people. So anti-symmetry is not going to work out as is a sibling of. But reflexivity is also not going to work out hmm, because one is not a sibling of oneself. So we have both C and D as a contender, but I'm going to try C. Ah, okay. Oh, okay, I see. Okay, this is tricky because it does acknowledge that sibling is not anti-symmetric. Reflexivity is the more fundamental property typically discussed as missing in this social relation. Okay, so that's why I call this one a little bit tricky because I knew that both anti-symmetry and we excuse me, and because I knew both anti-symmetry and reflexivity uh, do not apply in this case. I just did not know how it ranked between these two. So this one is a little bit tricky. All right, so done here. Um, and but the important part of this exercise is how easy it is to create your own exercise, and you can add some more description. When you create your exercise, you can focus on certain concepts. You can make it extra tricky. You can make it a little bit easier. You can make it kind of more like a scaffolding kind of sequence. Okay, starting with some easier questions and then kind of transitioning to some harder ones. So you can, by adjusting your prompt, you can actually generate various types of exercise for yourself. All right, so it looks like that's enough time for this recording. So I'm going to upload it and make it available at about noontime. All right, well, you guys have a good day staying at home. I hope most of you are doing, and I'll see you on Wednesday.